In this video, I will talk about the volume flow rate. The quantity that we call the volume flow rate is defined as the volume of the fluid that passes through a cross-sectional area over the time that it takes for that fluid to pass. So the letter Q is what we use for the volume flow rate. Now, the numerator here in the fraction, okay, this is volume, and the units of this, of course, are meters cubed, and this is time, and the units of the numerator are seconds. So the units for the volume flow rate will need to be meters cubed divided by seconds. Now, I will not go through the proof, but you can somewhat easily show that the volume flow rate can also be calculated if you know the speed of the fluid and the cross-sectional area of the fluid, of the tube, or wherever the fluid is flowing. So the first here, this is the speed of the fluid, and A is the cross-sectional area. Now, I want to remind you that the units of speed are meters per second, and the units of area are meters squared. So if you see meters per second times meters squared also gives you meters cubed per second, which it should. The units at the end should be the same on Q, delta V over delta T, the speed and the area, the speed times the area. I do want to emphasize here to try to not be confused with the two symbols here that appear to be the same. This uppercase V, this is volume, and the lowercase v, the magnitude of this lowercase v, this is the speed of the fluid. Now, the way that you can calculate the volume flow rate, because I'm giving you two expressions, you can use both of them. Sometimes the problem will tell you what the volume is in meters cubed, and the time that it takes for that volume to pass through a cross-sectional area. Sometimes they may give you the speed and the area itself instead of volume and time. But in either of those two ways, you can calculate the volume flow rate. Now, what is important when we deal with fluids? Assuming, okay, I will make the assumption that my fluid is incompressible. And what that means is that I cannot squeeze the fluid, I cannot compress it to make it take less space. Okay, you cannot fit the fluid that you have into a smaller volume by squeezing it. This is what this statement means. If I make this assumption, then if I call this, let's say, point 1, location 1, and I call this location 2, because the fluid is incompressible, the amount of fluid that goes through the cross-sectional area here at 1, I can show you. The amount of fluid that goes through here should be the same as the amount of fluid that goes through that part. This means that the two volume flow rates should be the same. The volume flow rate at 1 needs to be the same as the volume flow rate at 2. Now let's see what that means. The speed at 1 times the area at 1 should be equal to the speed at 2 times the area at 2. Now, let's see. The cross-sectional area at 1, this is large, whereas the cross-sectional area at 2 is a small number. We can see here this has a smaller diameter, a smaller radius, so the cross-sectional area needs to be less than what you have here. Now, because you have a large area on the left side and a small area on the right side, this means that the speed on the right side needs to be large and this needs to be small, so that a large number times a small number, you can make it equal. You can set it equal to a large number times a small number, okay? The speeds need to compensate for the difference in the cross-sectional areas. Now, we can think about this a little bit. If this means that the fluid here will have a relatively lower velocity than what it does here. If I think a different example, let's say instead of thinking in terms of fluid like water or some other fluid flowing, if you think about cars, let's say you have this is a highway, let's say an interstate, and you have, let's say, 10 cars passing from here every second. Okay, from this point. You're here, you're counting the cars, you're counting 10 cars every second. Now, assuming that there is no pileup of cars anywhere here, meaning my fluid is incompressible, there's no pileup of cars anywhere, the number of cars that you measure here per second, you should measure the same number of cars here. How many cars enter need to be equal to the how many cars you have exiting this space, assuming that they don't pile up anywhere. This is what we mean when we say that the volume flow rate is the same at 1 and 2. How much fluid you have going in, you have the same amount of fluid going out. Now, if here you can fit 1, 2, let's say 3, 4, 5 cars, but here you can fit only 2. If you want to have 10 cars passing per second, then here these cars need to be going fairly slowly to pass in 1 second. Whereas if you see here, if I want 10 cars to pass, these guys need to move significantly faster in order to make it to point 2 in 1 second, compared to here where you have only two rows of cars. The same idea is true with the fluid. If you want a specific amount of fluid to pass through one, because the diameter, the area is so large, the fluid will be moving slowly. But if you have a small cross-sectional area and you want the same amount of fluid to pass through this point in 1 second, the fluid here needs to be moving fast. This is what this expression is telling us, and this is what we call the equation of continuity. This is known as the equation of continuity. Now, an example can be if you're given the speed at 1 and the area at 1, and you're given the area at point 2, then you can find the speed at 2. Let's say I have this is taking place on the ground, and you have a river or whatever, a small river, and we have a cross-sectional area let's say, of 45 meters squared. Now, if at 1, so this is at location 1, the area is 45 meters squared, and the speed at 1 is 1 meter per second, then at location 2, if I know that the area at location 2, let's make that 22.5 meters squared, then I can find what is the speed of the fluid at location 2 by saying assuming my fluid is incompressible, the two volume flow rates need to be the same. So V1 A1 is equal to V2 A2, and from here you can say the speed at 2 will be the speed at location 1 times the area at 1 over the area of 2. Now we said the speed at 1 is 1 meter per second, the area is 45 at 1, the area at 2 is 22.5 meters squared, and because 45 is 2 times that, this means the speed at location 2 will be 2 meters per second. And you can see now, using the numbers, you can see, because I made the cross-sectional area smaller, I made it half of the cross-sectional area at 1, the speed at location 2 had to double to compensate for that decrease in the area. So this is how you use the equation of continuity and the volume flow rate. Now I do want to mention some problems. Okay, here I gave you the two areas and one speed that I asked you to find the speed. It is possible you will encounter problems where you will be given, instead of the speed and the area, you will be given the volume and the time, and then you need to say that the volume flow rate at 1 and 2 are equal, and then you proceed from there.